Hi, I'm Ravindranath Viswan, an application scientist at Denton Vacuum, and my co-author, Dr. David Douglas, is a senior product manager. Today I'm going to describe to you Denton's plasma ion beam assisted chemical vapor deposition process, in short, the PIB-CVD process, and the technology that has the potential for a wide variety of applications. In particular, I'm going to show you some results on organosilicon thin films that are not only great candidates for thin film encapsulation layers in OLEDs, but can also be used for a variety of applications such as mobile cover glass and hard coatings for automotive transparencies. The outline of my talk is as follows. I will first give a brief introduction to our company, and then we'll go into some facts about the organosilicon compounds and the importance of organosilicon thin films for display applications. This will be followed by some details of our patented large area linear ion source and the plasma ion beam assisted CVD process. Then I'll show you some recent results, and finally we'll summarize the main takeaways. Now for the introduction to our company. Denton Vacuum has been a pioneer in the thin film industry for over 50 years. We have a strong commitment to R&D and a large installed base, over 5,000 systems for a wide variety of applications, including displays, lasers, IR detectors, to name a few. We do all our manufacturing in the US and have a global footprint. Now let us look at some facts about organosilicon thin films. Organosilicon compounds are basically compounds that contain carbon silicon bonds. They have an inorganic part and an organic part, and they can be used to make hybrid organic inorganic materials. They are most commonly deposited by CVD or PECVD from organosilicon compounds such as HMDSO, OMCATs, TIOs, etc. And the film properties are tunable from a polymer-like to silica-like or DLC-like coatings. So they can be used for a wide variety of applications, such as in interlayer dielectrics, OLED encapsulation, mobile cover glass, hard coatings, and hydrophobic coatings, to name a few. The importance of organosilicon thin films for display applications is, as I mentioned before, because of coexisting organic inorganic functional groups that can be tuned to different degrees of hybrid organic inorganic properties by adjusting the oxygen HMDSO ratio during the process and the oxygen content in the film. A higher ratio produces a rigid and hydrophilic silica-like film, while a lower ratio tends to create soft and hydrophobic polymer-like film. Using our PIB-CVD process, we could even adjust the ion energies with lower oxygen ratio to tune the composition from a polymer-like to a DLC-like coating. And this is the work done at Applied Materials, where they show PECVD coated multilayers consisting of silicon nitride, plasma polymerized HMDSO buffer, and silicon nitride structure for flexible mobile device applications. They show a flowable buffer film that can cover a particle without leaving any voids or diffusion channels around it. And here they show a non-conformal step profile leading to planarization of surface irregularities. Now, while these films have excellent properties for thin film encapsulation layers in OLEDs, with Denton's PIB-CVD process, there is greater tunability of properties and potential for a wide range of applications, not only for flowable, soft, thin film encapsulation layers, but also for hard, highly hydrophobic, and optically clear coatings. The core technology here is our large area linear ion source. This is the schematic of our linear ion source. This is an RF source that operates at a frequency of about 2 megahertz. The basic elements of this source are a rectangular RF coil, which is powered by a RF generator, and it produces an inductively coupled plasma from source gases such as argon and oxygen that's injected into the source through a gas distribution tube. and the ions are accelerated to the substrate through a grounded single extraction grid, and by a pulse DC bias that's applied to the source body, and the precursor gases are delivered outside the source and right in front of the substrate, and the so and no neutralizer is required as the beam is self-neutralized, and the source is thus clean and can be used for long production campaigns. More importantly, the ion energy and the ion current density can be independently controlled, as is shown here. The ion energy can be controlled using the DC bias voltage, while the ion current density can be controlled using the RF power. What is shown here is the ion energy distribution for three different applied DC bias voltages: 0 volts, 100 volts, and 150 volts. There is a four-fold increase in the peak ion energy as the DC bias voltage increases from 0 up to 150 volts. On the other hand, there's only a 25% increase in the ion current density as the DC bias voltage increases from 0 up to 150 volts. In fact, ion energies as high as 500 electron volts can be obtained, although not shown here, eliminating the need for substrate biasing. Thus, the PIB-CVD process using Denton's linear ion source is more advantageous than conventional PECVD systems, because in order to get higher ion energies in PECVD, the substrate has to be biased, and substrate biasing can lead to thickness non-uniformities, especially when the substrates are insulating, when they are not flat and have inherent thickness differences, giving rise to differences in the electric field uniformity. So the PIB-CVD process has greater benefits for large area coating. Since there is no need for substrate biasing, the source can be used in an inline system as is shown here. The main advantage is large area coatings at low substrate temperatures, so it is very suitable for roll-to-roll coatings on flexible substrates. Since the precursor gases are delivered outside the source, there is less source contamination and longer operation times between maintenance. Now, this type of geometry is possible only because there is no need for substrate biasing. In fact, roll-to-roll coating would be very hard to implement or almost impossible to implement with substrate biasing. So what we have measured here is the substrate temperature as a function of the transport speed of the substrate, the linear transport speed of the substrate for a given ion energy and ion current density. And what we see here is, first of all, the temperatures below 100 degrees centigrade, which means it's very suitable for plastics and flexible substrates. And moreover, when you increase the speed of the substrate, the temperatures can be further reduced. So that's a very important thing when it comes to coating flexible substrates. So now we'll go into some of the results that we have obtained recently. All these coatings were done using HMDSO, argon, and oxygen. So what we show here is that a wide range of tunability of film properties can be obtained by varying the process conditions. For example, what we see here is the static water contact angle and the nano indentation hardness plotted as a function of the bias voltage, the pulse DC bias voltage that increases the ion energy. So as the bias voltage increases, what you can see is that the nano indentation hardness changes from less than 1 GPa all the way up to about 13 GPa, and the water contact angle decreases from about 100 degrees to about 16 degrees. So you can actually tune the film from a polymer-like coating up to all the way up to a hard DLC-like coating. And also, in addition, you can see that the optical transmission is can be changed by changing the oxygen argon ratio. So By increasing the oxygen ratio, you can see that the optical transmission increases from about 40 to all the way up to 90%, and the nano indentation hardness decreases from about 14 GPa down to about 8 GPa. So the film can be actually tuned from a hard DLC-like coating all the way up to a silica-like coating. In fact, a wider process parameter space could be explored by varying other parameters like the oxygen HMDSO ratio and the process pressure. So there is scope for more tunability. So one of the applications that we were targeting was for hard coatings on glass and plastic substrates for mobile cover glass applications. And So the coating had to have a hardness as good as glass, so greater than 6 GPa, and the optical transmission greater than 90%, and water contact angle greater than 90 degrees. And this is the summary of the properties that we have obtained so far. So what I have done here is plotted the optical transmission and the static water contact angle as a function of the nano indentation hardness. And you can see for a hardness of around 6 GPa, you can get a water contact angle of around 90 degrees and an optical transmission of around 90%. So but see, these are single layer films, and in fact, their properties can be further enhanced by a proprietary surface treatment process using the same ion source that we have demonstrated. So this is the effect of the surface treatment process on the water contact angle. What we show here is that we can increase the water contact angle by about 10 to 20 degrees with the surface treatment process. So in this case, it's around 20 degrees, and in this case, it's around 10 degrees. So this process is very suitable for increasing not only the water contact angle, but also for increasing the optical transmission. So using lower ion energies, we can coat soft polymer-like coatings. These are hydrophobic coatings and have very good adhesion to the substrate. What I have shown in this bar chart is a comparison of the water contact angle of the coated and uncoated substrates. Several different substrates were tested, and in all cases, the water contact angle greater than 100 degrees was obtained both on glass and plastic substrates. On the other hand, using higher ion energies, hard coatings could be obtained on plastic substrates, for example. The goal here was to increase the hardness of plastic surfaces for application in abrasion-resistant coatings for automotive transparencies. In order for these coatings to have good adhesion to the plastic substrates, a multi-layer coating was deposited by changing one or more process parameters. This bar graph shows a comparison of the nano indentation hardness of polycarbonate and acrylic substrates. And as you can see, the DLN coated substrates have a hardness that is several times higher than the uncoated or even the substrates with the commercially available standard hard coat. And also the static water contact angles are higher for the DLN coated substrates compared to either the uncoated or the standard hard coated substrates. In fact, these surfaces could be made even more hydrophobic by the surface treatment that we mentioned before. PIB-CVD hardcoats can eliminate a common process step in PE-CVD hardcoats. This is because most PE-CVD hardcoats require an adhesion layer which is commonly applied by wet chemical methods. However, as shown here from the cross-hatch tape test, PIB-CVD hardcoats have good adhesion both to the substrates with the standard wet chemical hardcoat as well as to the uncoated substrates. Now, this is possible with our PIB-CVD process only because of the wide range tunability of ion energies. So a multi-layer structure can be deposited directly on uncoated plastic substrates to transition the hardness of the plastic surface from polymer-like to glass-like. Now I'll summarize the main takeaways. In summary, a wide range of tunability of properties was achieved using Denton's patented linear ion source, which has the capability for independent control of ion energy and ion current density. There is a potential for a wide variety of applications due to the ability to deposit gradient coatings, multilayers, and the added advantage of plasma surface treatments, all using one source. Organosilicon thin films deposited using Denton's PIB-CVD process has a wide range of tunability of properties suitable for a large number of applications from displays to automotive transparencies. Film properties range from polymer-like soft coatings to hard DLC-like or silica-like optically clear coatings. Our linear ion source and the PIB-CVD process is also scalable for high volume production. Thank you, and I look forward to your questions.